Hello world, it's Siraj. Good to see everybody. Let's do this. We're gonna talk about recurrent nets today. So where all my homies at? Where all my homies at is my question. I have so many questions and not enough answers. Siraj, how far are we from solving intelligence? Anywhere from 5 to 10 years is my best guess. Let me mute this. I don't want to hear myself. I mean, I do, but not through the audio. Okay, so we're 5 to 10 years. I would say. I would hope. I mean, things are moving so fast. Yo, 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 yo. Okay, so welcome to Bollywood. Okay, hi, Bonnie, Rocio, Henry, Shivam, Duan, Arya. TensorFlow versus PyTorch. Arya, that's a great question. I am starting to like PyTorch, and in fact, the machine learning community is starting to say good things about PyTorch. That debate is happening right now, which is crazy because TensorFlow has so much momentum, but it's a good sign of showing just how fast things change in this field. Nothing is concrete, okay? How should I start machine? So yeah, so 5-minute Q&A, right? So hi, Pocket Man and Vishwas. How should I start machine learning? Watch all of my videos. Really, there's this guy who just commented on one of my videos, a genetic algorithms video, and he was like, I think his name was Fernando, but he was like, you started me on the path for data science. And now, after watching all your videos, now I understand every line. And before I didn't know anything. So really, watch my videos, all of them. Hi, Siraj, notice me. Vuk, hi, how's it going? Mohammed, hello from Russia, Moscow. Izdarova, Dadny Znayk Ruski, Ty Holodny Slaviansky Ubitsa. Ricardo, Sir Hamster. Okay, so we got a lot of people. Throw those questions at me. Because today we're talking about recurrent neural networks, and we're going to focus on the memory aspect. That's what we're focused on, because it is really important to talk about the memory aspect. Notice me, Senpai, I'm here. Yon, Tesla stock. Hello from Paris, Poland. Man, Afghanistan. Wow, we have Hungary. Oh my God, this is awesome. Okay, guys, let's talk questions. Can I start deep learning with no experience with machine learning? Yes, absolutely, but you do need some experience with math. So I would suggest introductory courses in statistics, calculus, and linear algebra. But what I'm trying to do is teach those things on the side as well. So, just use those as reference material. Finland, Chile, Brazil, Canada, Benvenido, Canada, maple syrup, how's it going? Justin Trudeau. Okay, I'm the only data science in Afghanistan. Okay, RNNs are better than life. No, but they're close. What's the difference between a CNN and an RNN? CNNs are a whole different architecture. You have pooling involved, you have convolution, you have strides. They're focused on images, and actually recurrent nets can be used for images, but we use them most of the time for sequential data. Really, everything is sequences in life. All data is sequential. Columbia. Okay, what's PyTorch? PyTorch is a new library. It's similar to TensorFlow, but different. And I'm going to definitely make a PyTorch in 5 minutes video soon. And I know it's going to get a lot of views, but not yet because we are focused on this torch. Don't worry, we're going to talk about PyTorch later. And I'm sure it's going to get more and more popular over time because all the cool kids are talking about it. You need a statistic about your subscriber nationality. We have over 200 countries represented in this community. 200 countries. It is fast becoming the largest machine learning community in the world. So it's very exciting to be here right now. What do you think about Profit by Facebook? So I saw that library, and I have to look into it more. I didn't really read the details. AWS or Google Cloud ML? Great question. So AWS recently went down. It went down because for whatever reason, and then all these apps that we use just went down because of them, because everything is based off of AWS. But that's just a problem of centralized systems in general, and it shows why we need decentralized systems. That's a whole different topic. I wrote a book on that. I could talk at length about that, but we're not going to. But comparing those two, I would say AWS because it's got more people using it, and it's I don't know. I'm used to AWS, and the customer support is also pretty great. Favorite subject in school, math? Honestly, it was English. English was my favorite subject. I love language. I love writing. I consider myself a technical writer and an engineer and a data scientist, but English was my favorite subject in school, followed by close second math. Close second was math, absolutely. I remember being super excited by math and having a hard time understanding it in middle school, but I was just so excited about it that excitement is really what pushes you through the obstacles that you'll face. One more minute, and then we're gonna get started with this code. It's an IPython notebook. OpenAI and TensorFlow don't compete. They're not competing. They're complementary. dude, why no Twitch? Why? Because I just like to have it on YouTube because I don't know. We'll see. I mean, if someone can convince me to use Twitch, I will, but I'm not sure why. How do I build up CV for Google internship? Have projects on GitHub. I'm actually going to release a video on job interviews this weekend or next weekend, so stay tuned for that. One more question, and then we're going to get started. Which one do I want to answer here? How to use, okay, this is a good one. Pocketman said, how to know when to use LSTM and when not to. LSTMs generally improve our prediction every time. I mean, all of the greatest advances coming out of sequential learning involve LSTMs right now in some way. And Andre Karpathy's blog post is so epic, The Unreasonable Effectiveness of Neural Networks, and most of that uses LSTMs. Use Twitch so we don't have to watch live programming at 5 FPS. Okay, so that's a good reason. Okay, so I'll think about that for next time. I'm continuously trying to improve my live stream. So okay, so we've got 333 people here right now. So let's get started with this code. We don't want to keep people waiting, okay? So let's get started with this. Let's talk about what we're going to do. Let me just say what we're going to do first. We're going to build a recurrent net that takes in 2 sequences, okay? So one sequence is a binary sequence, right, of 1s and 0s. And meet your arch nemesis, Niraj, hi. And the other sequence is the same sequence but shifted, okay? And we'll talk about what that shift means, okay? But the idea is that we're going to map these 2 sequences together. We're going to learn the mapping between these 2 sequences using a recurrent neural network. So let's get started with this, okay? Let's start broadcasting, guys. We have so much sequential stuff to learn right now. We're going to dive into recurrent nets. It's going to be awesome. Screen share, okay? Screen share. Here's our screen that we're going to share. Now, I have the notebook in the GitHub link in the description for this video because you guys have been asking for that. So, you know, I thought it would, honestly, I thought it would be funner. I thought it would be funner if you guys don't see the code, but you know what? You'll see it as I code it, but you know what? I'll just give it to you anyway. So that's that. All right. So here we go with this. Here's the notebook, and I'm going to code parts of it, and parts of it are not going to be coded. So it's going to be a mix of both. Let's make it a little bigger, okay? Make it a little bigger, okay? Or a lot bigger, one or the other, okay? So that's what we're going to do with that. Let's get the comments over here, and we're going to start building this. So everybody pull up a notebook, okay? It's in the link, and we're going to talk about what is happening as we go getting started, okay? So here we go. What we're going to do is we're going to use a recurrent net. Oh, and also, of course, I need to have my face up here. What am I doing? So what we're going to do is we're going to build a recurrent neural network, and we're going to build it with Tensorflow. We're going to build a recurrent neural network with Tensorflow, okay? And we're not going to use any other libraries to build the network. I mean, we're going to use some libraries, but they're not going to be to build the network. They're just going to be there because, you know, they're to plot the data, okay? Okay, so let's get started with this. So what is a recurrent neural network? It is a type of neural network that is used for sequential data. We're going to learn about sequential data right now. And this is a great paper that I have linked right here that talks about recurrent nets. Definitely check out that paper after this live stream, but not right now. It's probably the most comprehensive paper on recurrent nets that I found. And remember, when you read a paper, remember to read the abstract first, okay? Don't expect to understand everything from a paper. Just read the abstract and then keep on going, okay? And if you understand the abstract, that is a achievement in and of itself. So we're going to start off by importing our dependencies, right? We're going to import IPython's display function because we're going to be displaying images. These images are going to help us look at what we're doing. NumPy is going to help us generate some binary input data. TensorFlow is obviously for machine learning, and then Matplotlib will help us plot this data. So I'm going to start off by showing this image, okay? Now what this is it is an image that shows a recurrent net that is learning over time. So it's learning over time, and these 3 squares are the states of the hidden state. So that is that hidden layer in the recurrent net over time. So it changes over time, right? Why? Because we feed it not just the input data, we feed it the input data and the previous hidden state. So when we perform an optimization technique like backpropagation, it's essentially backpropagation through time. We're just getting started, so you didn't miss anything. It's backpropagation through time. So it's like Back to the Future. You know, it's like time travel, and we'll talk about not literally time travel, but in a way because we remember what happened beforehand. we're going into the past. Okay, so that's what this is. So let's get started with this. Okay, that's the definition of a recurrent net. Now what we can do is we can start coding this thing. So we're going to start off by coding up our hyperparameters. Okay, so for our hyperparameters, we're going to define a number of epochs, which is 100. Remember, so whenever we're training a network, we define epochs, and inside of these epochs we have batches. So for like 10 epochs, we'll have like 5 batches. So it's like 50 total iterations, right? 10 times 5, because it is a nested loop, right? So for every epoch, how many batches do we want to train against? So we're going to define that number of epochs, and obviously the more epochs, the longer the training, the better our prediction, right? So it's a trade-off between computation, time, and accuracy, like all things when it comes to machine learning. Truncated backprop length. So the next variable, the truncated backprop length, I'm going to talk about in detail when we get to it. But right now, let's skip that, okay? So for our state size, it's going to be 4. So what is our state size? The state size is the number of neurons in our hidden layer. Okay, so that's what it is. So because we have a 3-layer recurrent net that we're building, and that hidden state is what we're going to update over time, and we're going to talk about how that works. Then the next one is going to be number of classes. So by number of classes, since our data is binary, there's going to be 2 classes. But this isn't classification. It's a sequence-to-sequence mapping. The number of classes is 1 and 0, so it's 2. Then we're going to talk about the echo step. The echo step is going to be 3. And so the echo step, I'm going to talk about that one in a second too. So remember, these are the 2 variables that I'll talk about when we get to them. The truncated backprop length, and then the echo step. And so the next one is going to be the batch size. So the batch size, remember, inside of each epoch, we have a number of batches. So we're going to define it as 5. And then lastly, the number of batches. So the number of batches is going to be the total series length, and we're going to take the quotient, right? So in Python, this character means quotient, by the batch size, and the quotient of that by the truncated backprop length. And this is going to make sense when I talk about truncated backprop length in a second, but let's go ahead and just type that in first, okay? So that's going to define the number of batches we have, okay? So let's go ahead and get started with collecting our data set. What we're going to do is we're going to generate this data, and this is a good step to talk about. Like, generating the data is a good step to talk about, because a lot of times we just want to test out our neural net, but we don't want to test it out on real world data, so we can just generate it ourselves using NumPy. And there's a lot of strategies to generate data, but what we're going to do is we're going to generate time series data. Specifically, we're going to generate 50K samples of time series data, and it's going to be all binary. Okay, so we're going to use the NumPy's array function to do this. Okay, and we're going to make sure that compiles. Right? Okay, so the NumPy array function is going to say, well, we're going to generate a random distribution of data using the random.choice function, and we're going to say we want 2 classes, the length of the series that we defined earlier, and then the probability that each of those classes gets picked is 50-50. Right, so it's the 50-50 chance that each number in the series, as it's generated, is going to get picked. That's what that is. And then, so that's going to be stored in X. And then what we're going to do is we're going to generate our echo. So let's talk about what this echo means. So we're going to shift this 3 steps to the left. We're going to shift this time series 3 steps to the left. And what do I mean by that? By shifting it 3 steps to the left, we're going to pad it with zeros. We're going to pad that data with zeros, because it's going to be the same exact series, but shifted to the left by 3 steps. And we're going to learn that mapping, right? We don't need any testing data, because it's going to be the same shift, right? So it's 2 sequences, and I'm going to show it with this image. This image is going to work, okay? So the roll function is going to say, so we have X and then echo step. So given like 2 numbers, like say like 2 and 10, it's going to start 2 from before 10 and then n before it. So it's going to, so the output of this line right here is going to be, so if it's like 2, 10, right, X is 2 and echo step is 10, it'll be like 8, 9, 1, 2, 3, 4, 5, 6, 7. Okay, and then the reason we do that is because now we're going to pad the beginning with zeros. So we'll say Y and 0, and then echo step, and then finally we'll set all of those to 0. Okay, and then what we're going to do, yeah, lag by 3. Okay, so and then what we're going to do is we're going to reshape it, right? So we have 2 more lines of this generate data before we get started with our actual machine learning steps. So we're going to reshape this data so that it's formatted properly to feed into our network. We want to feed this into our network, and we have to format it properly, and NumPy's reshape function does this. It takes a matrix and it reshapes it into a size that we give it. Now, the batch size is what we're going to reshape it as, okay? So that's for y, that's for x, and now we're going to do it for y, okay? This is to have an x and y that are correlated with time, exactly, okay? Okay, so then for batch size, we have that, and then we have -1. Great. So that's our x and y, and then we're going to return those values. So let's visualize what this looks like by running this function once, this function that we just generated, generate data, and it's going to be stored in this data variable, and then we'll go ahead and print that data there. Let's see what this does. Let's see what this does. Yeah, I'm going to show the data. Here we go. NP is not defined because I didn't compile NP beforehand, right? I didn't compile this. Yes, let me compile that. Boom. Compile. Okay, and then compile the hyperparams, and then compile this function. Okay, so this is our data, right? It's just a bunch of ones and zeros. It's sequential data, right? And it's formatted to be a 2D matrix of points. And now we can visualize this. It's all ones and zeros, right? It's all ones and zeros, and so the x values and the y values are both ones and zeros. The x values are the initial ones and zeros, the binary data, the sequence of ones and zeros, and the y data is that same exact sequence, but shifted over 3 steps. And those first 3 steps are then replaced with zeros. And we want to learn the mapping between these 2 points. The point of this whole exercise is to learn about how memory is incorporated into a recurrent net. And that's going to be the really cool part, and that's what we're going to get to, okay? So that's the data that we've generated, okay? So this is an image that shows what this data looks like, okay? Basically, so this is an image of what the data looks like, and it's a reshaped data matrix, and the arrow is going to show so it's showing the time steps, right? So for every new row, it's a new time step. We can consider it a new time step. When we feed it in, it's going to be at a different time step, okay? So let's go ahead and get started with our actual machine learning with TensorFlow. So step one was to generate the data, and now step 2 is going to be to build this model. It's going to be to build this model. The point of reshaping the array, the tensor or array, whichever you want to call it, was so that we can feed it into our placeholder, which is that gateway that data flows into TensorFlow. Okay, so let's get started with our TensorFlow portion, right? Okay, so for building our model, the first thing we want to do is generate or to initialize both of our placeholders. We're going to have placeholders for our x values and for our y values. Okay, so for our placeholder, we're going to say, let's use our float. So what is the data type for our first placeholder? It's going to be a float 32 because these are 32-bit integers. And then we want the shape of it, right? So it's going to be a 2D matrix of 5 rows and then 5 columns and then 15 rows, right? Just like we saw up there. That's exactly what we saw. We want to fit it to be that, okay? And it's going to be truncated backprop length. Truncated backprop length. And remember, I'm going to talk about this in a second. It's truncated backprop length. But so that's the batch y and the batch x. Okay. So we're going to do that for both placeholders. And in fact, I could just copy this and paste it again because it's the same thing. Okay. For all those showing up now, you're not missing anything. Just look at the notebook so you can catch up. It's in the link. Okay. So that's both of our placeholders, right? So remember, in TensorFlow, these placeholders are gateways. This is what we feed our data into. These are primitive types. These are primitives in TensorFlow. Placeholders, variables, constants, these are the primitives with which TensorFlow works. And these gateways we feed in the input data and the label data. So we can consider this echo to be a label, right? In a way, it's a mapping between 2 sequences. It's a sequence to sequence mapping. Okay, and we're not using LSTMs because we have plenty of time to talk about LSTMs in future episodes. We're going to talk about art and video and music generation and sequence-to-sequence learning with chatbots, and all that stuff's going to be using LSTMs, and we'll talk about that in detail. But what we're doing right now is we're just going to generate these 2 placeholders, okay? So we have these 2 placeholders, and the next thing we're going to do is we're going to initialize our state, right? So this is the great part of this tutorial. This is what I'm really excited about. What we're going to do is we're going to show what really is happening in that state, right? It's not some magic. It's not just, right? We're going to show what is happening in the memory portion of that hidden state. So we're going to initialize a state because we feed in the state every time as well, right? That's the great thing about recurrent nets, right? We're not just feeding in input data every iteration of training. We're also feeding it in the previous hidden state that was learned. So this is the gateway for that hidden state. So in a recurrent net, we have a placeholder not just for the input data and its labels, but also the state that it learned beforehand, right? So it's got a previous state and a current state. Okay, so that's what our placeholder is for. And what is its type? It's going to be just like the other two. It's going to be 32 bits. And then the shape of it is going to be the batch size and then the state size, right? And we define the state size as the number of neurons that happened beforehand, okay? So batch size and then state size. So we've defined these. Great. Okay, and then now, of course, we have a type error. So let's see what we got here. D-type. So, you know, it's good to see this errors happening in real time, right? So for D-type, it's placeholder, shape 54, float 32. What do we got here? What tf.float 32, batch size, state size. We got placeholder values. And this one is, oh, so you know what this is? This is actually an int 32 because, I think, right? Oh. All right, great. Okay, so that's it for our state. Okay, so now what we're going to do is we're going to build our weights and biases for this network, right? We've got our placeholders. We defined the gateway. The data is ready to be fed into the network. Now let's define those weights and biases and talk about what is happening. Yes, so we're going to talk about what happens to the state. It's going to be dope. It's going to be so dope because you never really see this part. So I'm really excited about that. But let's go ahead and define our weights. So remember, because it's a 3-layer network, we have 2 sets of weights, right? Those are the weights between the hidden state, right? The input from the input layer to the hidden state, and then from the hidden state to the output layer, right? So there are 2 weights. So let's define those 2 sets of weights. So the first one is going to be a W value. We'll call it W. And we're going to use the tf.variable for this. And why do we use tf.variable? Because it's that TensorFlow primitive, right? And variables can be updated over time, right? Unlike TensorFlow constants, variables can be updated over time. And that's why we're using a tf.variable. We're going to randomly initialize this value, okay? And we're going to use a state size +1. And okay, so this is the distribution of values. It's going to be a random distribution of values that's going to update. Now, why do we initialize our weights as random, right? Why don't we just set it to 0? We generally, in the papers that get the best results, it's kind of become commonplace to initialize weights as randomly, right? But there could be better, ways of doing that in the future. But right now, randomly initializing weights seems to work best. So we'll now define the data type for this, which is going to be tf.float32 again. Okay, so that's it for the data type is going to be tf.float32. Okay, so that's us randomly initializing our weights, and then we're going to initialize our biases. And so for our biases, why do we even have a bias? So biases, what they do is they improve convergence. And when we think about biases in terms of, so I'm typing and talking and teaching at the same time, this is dope. I'm really getting better at this, guys. Like just doing this every week is really, it's just public speaking, basically. I'm just giving a speech every week. So what happens is for biases, we're improving convergence. That's what it does. So we can think of biases in terms of linear regression, right? So in linear regression, biases, you can think of it as the y equals mx plus b equation, right? It's very simple to think about it in terms of a linear model. It's harder to think about it in a non-linear model. In a non-linear model, biases still offer that constant anchor point, such that it improves convergence. But it's not that it's a y-intercept per se. It's just like an anchor point, so that the values that we predict aren't too far off from what they should be. And we can talk more about biases in a second. Right, the delay could be quite long. So that's it for our initial set of weights. So weights and biases 1, weights and biases 1, and then weights and biases 2. Biases 1, and then weights and biases 2, right? So weights 2, biases 2. So, and second set. Okay, and so the difference between both of these and second set. And so the difference between both of these is going to be the state size, not +1, and then the number of classes, and then finally the data type is going to be set to float 32, and then the number of classes, right? Because it's going to be 1 or 0, okay? Because that output, and the reason it's going to be num classes for this one is because we're going to output that set of classes, right? Okay? Okay, no, I can slow down. Don't worry about it, I'll slow down. Okay, so that's that, okay? We define this, okay? So now this is what, so we define our weights, we define our biases. It's a lot to remember, but at the same time, just taking all this in cerebrally, continuously is good. Like there's a lot of things that we're learning even subconsciously that we don't even know, okay? So it's good to even take these things in cerebrally. Even if you don't fully understand it, you know, at the start, you will slowly start to get it, okay? So we define those biases. Now what we're gonna do is we're going to look at this image, right? And so so we could think of this as as batches, right? So we have a full matrix of binary values, and we're going to look at this in batches. We're going to look at this in batches. So not all of it, we're not going to feed it in all at once. And so that's what this dotted square over these values is. It's kind of like looking at the batches, okay? So let's keep going. So now what we're going to do is we're going to unpack these columns, and so we can feed it into our array. Okay, so unpacking is for what we're gonna unpack these columns into a set of lists, and each of these lists are going to be fed in, right? So remember that matrix of 1s and 0s. We just want one array, right? So at a time, we just feed in one of those arrays one of those sequences at a time. Unpack matrix into one-dimensional array. I mean, right? So so for our input series, and we're going to do that for both of our values. We're going to do it for our input series, and then we're going to do it for our output series. And we've defined those placeholders for each, right? And so it's going to be on a single axis. And what we can do, the end goal here is to map two sequences together, right? We have one sequence and another sequence, and we want to map them together. Like, what is the mapping? Like, what is the correlation? What is the relationship between these two sequences? And neural nets are universal approximators. They can find a mapping between. They can learn a function that maps between two different values or sequences. Okay, so we define placeholders for both of these, right, so batch y placeholder. Okay, great. And let me make sure I named that right. Okay, great. So then batch x is not defined because I need to say batch x is placeholder. And here we go. So that was it for that. And then they said that access equals 1. Access equals 1 is the value for the unpacking of everything. Unpacking the values. What are you talking about here? Access equals 1, not in -1 to 1. And here we go with that. Let's see. You crazy Python interpreter. You crazy. Okay. What are you talking about here? Okay, so interesting. So what's happening here is the value shape is. Let's see. Should I debug this, guys, or should I keep going? This is your call. I can continue to debug this, but I also don't want to waste people's time. Let's see. Okay, so what we're going to do now is we're going to think about this. So what is our input here? Debug. Okay, debug. Keep going. Debug. Debug. Okay, so debug. Awesome. No debugging. Man, people are split. I just got to make a call here. Keep going. Debug. It's helpful to see debug. Okay, so debug. Let's debug this. So So what did we give it? We gave it batch X placeholder and then batch Y placeholder. Oh, and so let's see. So these placeholder values could be updated, right? So okay, so what are these placeholder values? So for our placeholder values, let's update these. And then let's see, do that again. Do that again. Do that again. Great. Okay. Okay. So it was those placeholders. What happened was for the placeholders, I needed to define the type. Okay. So let's keep going. Debug and send nudes. Oh my God. We got some. Okay. So here we go. So current batch split into. So this is what it looks like, right? So we've split our two-dimensional our matrix into feedable one-dimensional arrays. That's what we've done. Okay. So that's what we've done. So now what we're going to do is we're going to, let's see, what is the next step? Now we're going to, okay, so this is the cool part. This is the part that I've been waiting for. This is the part, okay, this is the part right here, the forward pass. This is what we learn about memory, okay, and how memory is incorporated into a recurrence net. That's what we're about to do, okay? So pay attention to this because this shit is awesome. So for our forward pass, we're going to start off by defining our placeholders, right? So our placeholders that we're going to update over time. Now, we could do this inside of our computation graph, but we're going to do it beforehand. Now, I mean, we could just have a gigantic computation graph, but we're going to do this beforehand. So we'll define our current state, that is the state of the current hidden layer, as the initial state that we defined beforehand. And it's about recurrent nets. So what we're going to do is we're going to track this series of states over time, and we're going to store it in this array. So it's not magic, guys. It's not magic how we remember this hidden state. We store it in an in-memory array. So let's go ahead and do this forward pass, right? So remember, whenever we're this is what recurrent nets are all about. So what this is it's a forward pass through the network. This is, right, we have a forward pass and then a backward pass where we update our weights, right? So what we're going to do is our forward pass first. So for all of the inputs that we have that we defined beforehand, we're going to take the current input, okay, and we're gonna take this input and we're gonna feed it through our network, right? And we define our weights and biases. We can just give it to that. So we're gonna take the current input and we're gonna, first of all, we're gonna reshape it so it's into a shape that our recurrent net accepts. So it's gonna be, we're gonna reshape that current input into the batch size, okay, into the given batch size, and the other. So this is the shape 1. Okay, so this is the shape that we're going to give it in. And then what we're going to do, guys, we're going to do so many gaming videos later on. We just need to get through this course first, okay? And then what we're going to do is we're going to mix both the input state and the input data. All right, so we're going to say input and state concatenated. Now, what this variable gets, it's going to be the concatenation, which is a computer science term for combining two values together. Great word, use it in real life as well. We're going to combine both the current input, or that is that current input, which is the data, and the current state. And so how do we combine these two values? To combine these two values, we're going to use the concat function, which basically combines two tensors together. And so, and then what we do, okay, is we're going to perform our forward pass matrix multiplication to calculate our next state. So what do we do? Well, first of all, we're going to perform, to do this, we're going to perform a, let's talk about this. Let's talk before, so it's a nonlinearity, which is the tan H function. But before we squash our data with our nonlinearity, we're going to perform our matrix multiplication. That is what is happening at every layer of a network, right? It is a series of matrix operations that are happening, whether it be multiplying those weights by the input data, whether it be pooling those values, whether it be convoluting them into convolutional nets. It's all matrix multiplication. It's all linear algebra. Okay, so we're going to perform matrix multiplication, and TensorFlow does this very easy for this with this matrix multiplied step. And we're going to concatenate we're going to take that input and state value that's concatenated, and we're going to perform that matrix multiplication with the weight, right? That initial weight. So this is what's happening in the forward pass at the first part of our recurrent net. This is what's happening in that first part. And we're going to add the bias, okay? And that's what's going to give us our next state. Now, what are we going to do with this state, right? Well, we're going to take that matrix multiplied value and we're going to squash it with a nonlinearity, which is what we always do. Usually in a not just a recurrent net, but any kind of neural network, we have some matrix multiplication, then followed by a nonlinearity. So this could be a tan-H function, it could be a sigmoid function, it could be, what else is there? ReLU. There's a lot of different options. In this case, we're going to use a tan-H function, okay? Which is generally we see tan-H used a lot in recurrent nets specifically, okay? So, yeah, we got to ban these spammers. So we're going to, so sigmoids are great for generating output probabilities. So whether it's a convolutional net or a recurrent net, generally we see sigmoid at the end, at the last convolutional block or the last, last layer of a network to just output that value that's between 0 and 1 that describes our output probability. And sigmoid takes a while to converge. Tan-H is better for these. It's faster. Okay. Okay. So here's the cool part. So we define that state series empty list at the beginning, right? Now we're going to append it with the state that we've calculated. So we're going to append it with the next state value. We're going to keep doing this, right? So eventually, this list is going to be filled with a sequence of learned hidden states. This is the memory aspect of a recurrent net. We are remembering every step through time. We're gonna remember every hidden state's values. And it's not just that it just remembers it and then throws it into space. It stores them in a list. It stores them in memory, in a in-memory data structure. And then once we've done that, we set the current state to the next state. So as you recall from data structures and algorithms, this is very similar to a stack or a tree where we set the current to the next, right? It's kind of similar to that. It's very similar logic of continuously updating. Okay? So that's what that is. So that's our forward pass, guys. That's our forward pass. And what this is going to do is it's going to give us all of those hidden states and it's going to save them in memory. It's going to save them in memory. Okay? So, and watch there be an error. Okay? Batch's size is not defined on line 8. Unfortunately, I don't have line numbers in IPython notebooks, but let's see. Batch's size. What do we got here for batch size? And I'm going to do a 5-minute Q&A after this as well, okay? So stick through this and we'll get the 5-minute Q&A. So batch's size is going to be, where do we have batch's size? Oh. Current input, oh, right, batch size, not batch's size, duh. State series is not defined. Where are we? So that's for .append. It's called state series, duh. Okay, great. Okay, so we define that. Look at Chris' comment, batch's typo, thank you. It should be batch size. It should be, all right, thank you. Great, so we've got that, and here's an image of what is happening, right? So this is a way of thinking about it, right? So we are concatenating the current input with the current state value. And the concatenation occurs through a matrix multiplication operation. And then we squash it with a nonlinearity. But before we squash it, we multiply it by that weight value, okay? So it's a matrix multiplication, and then we squash it with a nonlinearity, and we get that next state. And we're storing all of those states through time, okay? Suraj, is the state saved for all hidden layers or only for some? It is saved for all hidden layers. It is saved for all hidden layers. Now, okay, okay. But not in this case. Not in this case. We could, but that would be very computationally expensive, right? To store, if our data was huge, storing all those hidden states would be very computationally expensive. So, and now I'm going to explain why we use that that value, which was truncated backprop length. So the truncated part means we're only going to save portions of that hidden state, that sequence at a time, and we're going to discard the oldest values over time, right? So it's similar to the vanishing. Remember in the vanishing gradient problem, the error becomes less, the error value is, less of it is sent back over time. So what we're going to do is we're not going to save all of those states because these layers are not going to be unrolled at the beginning of time. We're going to truncate at a limited number of time steps. So it's only going to, we're going to do this. It didn't happen yet. It will continually do this. Okay. Much love, AI aficionado. Okay, so now we're going to do the loss step and we're going to minimize the loss. Okay, so let's go ahead and we have our hidden states, we've calculated it, we've done our forward pass, and now we're going to do our backward pass. Okay, so this is the learning step. This is the learning step. Let me roll. I always roll up my sleeves for the fun parts. So let's calculate our loss first. So to calculate our loss, we're going to say we're going to define a variable called logits series, and then inside of logits series, we're going to say we're going to perform matrix multiplication between our state value and the next weight value, right? So we did we've done forward pass, we've done half of forward pass, and now we have to do the second part of the forward pass, right? So actually, we're not fully done with forward pass yet. We've done that first part, right? Now we got to do that last part until it gets the output, and then we'll do our backward pass. Okay. We are absolutely doing back propagation for this, and I'll talk about that when we get to it. So this is our next step, right? So our second set of weights and our second set of so this is in our second set of biases. So for every state we have in that states series list that we calculated, we're going to calculate the logit series. So logits is short for logistic transform. Okay, and so what we're going to do with this, these are the values that we are going to squash at the end. These are the outputs. This is the output values that we're going to squash at the very end with a softmax, and that's going to give us our predictions. Okay, so all of our logits we're going to squash with an ending nonlinearity, which is going to be a softmax function. Okay, this is our ending nonlinearity, and Tensorflow has this great built-in softmax function for logits in logits series. Okay, so this is going to be our list of all of our predictions. Okay, over time. Okay. We always use backpropagation for training. Backpropagation is the way to train neural networks, except I've only seen one paper that didn't do it, that DeepMind released, which was called synthetic gradients, and they didn't really use it more afterwards, which was crazy because at the time I was really excited. I was like, oh shit, backpropagation is obsolete now. But like in their next papers, they didn't really use that again. So we'll see. So yeah, backpropagation, we always use backpropagation for now until something better comes along. But okay, so let's measure our losses. We have our predictions across time, and now we're going to measure our losses. So for our losses, we're going to use the sparse softmax cross entropy with logits function. Now talk about long method names, right? If anybody's used Objective-C, you are right at home right now. We have a very long variable name here that I'm going to explain, and we're going to feed it the lot. What it's going to do is going to calculate our losses using, okay, and okay. So what do we got here? For all of our logits labels, let's see. For all of our logits, for all of our labels in the zip, logits series labels backpropagate to update weights. Backpropagate to update weights. So I was actually asked to speak at this Galvanize conference, and it was like they had as a speaker, and they had all these like lead data. It's like lead data scientists at Airbnb, lead data scientists at Square, and they asked me to rap. So I was like, and then Siraj raps. So I was like, let me think about it. So we'll see how that goes. Maybe I'm busy right now. Okay, so here's what this line does. Here's what this line does. Okay. So this is going to return a tensor. So actually, what this does is going to it's going to do exactly what we did before in this line right here. It's going to compute the softmax so we're actually doing this twice. It's going to compute the softmax. It's going to compute those probabilities for the logits and the labels. So for our sequence and for both of our sequences, right? And then it's going to perform cross entropy on them. And so cross entropy measures the difference between two probability distributions, okay? It is a method of measuring the difference between two probability distributions. And that's gonna be our loss. That difference is what we want to minimize. We want to minimize the difference between our output probabilities and our sequence, our label sequences, right? That echo, right? We want to minimize it different, and we're going to minimize it through an optimization function. Now, whenever you think about neural networks, everything is about optimization. It's about measuring an error value and optimizing it. Everything is an optimization. Everything is optimization. And in fact, in life, you start thinking about everything in terms of losses and optimizations. Whether it's a relationship with somebody, like how do you minimize your losses? How do you whatever you're doing, a sequence of steps in life of you want to optimize it. I'm getting a little off track. So back to this. Now we're going to minimize these losses. So this is going to calculate a list of losses. And what we're going to do is we're going to use the reduce mean function. We're going to use the reduce mean function to compute the average of those losses, okay, into one value, okay? That's our total loss that we've measured, okay? After one full forward propagation, this total loss is the output loss that we want to minimize, okay? Okay? The total loss. Now, what we're going to do is we're going to do our optimization step. Now, TensorFlow has a bunch of built-in optimization steps. And what we're going to do is we're going to use Attograd. Now, Attograd is a really cool. It's a really cool. Let me just type this out first. Total loss. Okay, so that's that input that we gave. So Attograd is a really cool optimization technique. Okay, so it's very similar to stochastic gradient descent. So what happens is there's some features so here's why we use Attograd. Sometimes there are features that are very important, but for whatever reason, our neural net doesn't weigh them properly because it uses the same learning rates across. So 0.3, by the way, is our learning rate that we're feeding this Attograd optimizer. So for some reason, the learning rate is the same across all of our features. So for some reason, it doesn't weigh those very important features properly because it's sparse. Sometimes sparse features can still be very important. So that is one of the cruxes of neural networks. If a feature is sparse, that means there's not a lot of data in a feature, but it's still important, then it won't recognize it properly. So what Attograd does is it uses different learning rates for those sparse features. And what this does is it gives them more weight. It gives them more importance in training. Okay, and because we have binary data here, we're going to use Attograd, okay? And I have a great paper on that, which is in the comments of the link. Great paper, notes on Attograd. It's actually very simple. It's not very simple. It's simpler than most optimization papers to read, so I've linked to it. And definitely check that out afterwards. But Attograd is basically, in a nutshell, it gives voice to the little guy. It gives voice to the little guy because the learning rate is adaptable, okay? Weights that receive high gradients will have their effective learning rate reduced, while weights that receive small or infrequent updates will have their effective learning rate increased, okay? So, but it's not like a magic wand, right? It doesn't always work, but right? So we generally want to try out different optimization steps, and having one line, right? We could just implement our optimization in one line, makes it really easy to try out different optimization steps, right? It's all about experimentation and trying out different options and seeing what works best. Okay, so that's it for our loss and then minimizing it. Okay, state series is not defined here because state series, not states. Great. Okay, so that's that. Now, this is the visualization step. So I'm actually not going to code out this visualization step because it's all it's not machine learning. Okay, so I'll skip this part. But basically, this is going to visualize what we see. Okay, and what it's going to do is going to plot the training input, the training output, and then the current prediction. It's going to plot out all three of those things. Okay. So that's the visualization step. Now we're going to get to the training, the computation graph. Now we've defined the forward pass, we defined the back propagation through the loss function, and then the back propagation step, which is the Attograd, right? So that is the optimization step to back propagate. Now we're going to train the network, and we're going to use those values that we've calculated through the forward and backward pass to do this training step. Okay. So in TensorFlow, we always define a section, right? Sections encapsulate our graph. Hi, Othan. So sessions encapsulate our graph. And we'll say session.run, and what we're gonna, so this is a really stupid step. I don't know why we have to do this. I mean, I don't see why. It should just know that all the variables we've initialized before are a part of this graph. I mean, what else will we use them for? So, you know, so remember, not all code was written by people. Nothing is perfect. Nothing was sent by the gods. But so, right, so it just shows that everything is not perfect. Okay, so, okay. So we're going to run this session, right, using the variables that we've initialized beforehand. Okay, so now we're going to say, let's define our plot, and it's going to be in interactive mode. And then we're going to say, let's initialize the figure. Let's initialize that figure value. And then we're going to say, show the graph. Show the graph. And then we're going to say the loss decrease. So we're going to map the loss over time, so we can print them out, right? We want to show all the loss values decreasing over time, so we'll initialize it as an empty list. Now we're going to go ahead and do our training iteration step. So, right, so we define those epochs, right? So the number of epochs that we had beforehand, and for each of those epochs, we're going to generate data. So, right, we define that generate data function beforehand, and it's going to output the sequences, right? The one is going to be that initial binary sequence, and the other one is going to be that copy but echoes, right? So it's shifted over. Okay, and then we're going to initialize our empty init the hidden state. So our current state is going to be initialized as an empty matrix. And we're going to use numpy's 0 function to initialize it, and the state size. Okay, that's our hidden state. Now we're going to print out that. I'll just take that one in. Okay, so now we're going to say for each batch, so in each of those epochs, we have a set of batches, right? So these batches are going to be inside of a range for all of those batches. And so I think we defined 5 batches. So for 5 batches in the number of epochs, we're going to define a starting and ending point for those batches. Okay, so a starting and ending point for those batches is going to use the truncated backtop length, because we don't want to remember all of the hidden states, right? We only want to remember hidden states, you know, the most recent hidden state. Because why? Because it would be computed. I'm going to definitely have a Q&A right after this is done in 5 minutes, okay? Give 5 more minutes before the Q&A, guys, okay? Stick with me here. So for truncated backtop length, we're going to say, okay, so that's a starting point and our ending point. And then we're going to define the starting point and the ending point. And what is that? Hi, Ashish. Okay. Batch Y, and then start IDX, and IDX. Okay, so these are our batches for our Y and okay, so I'm reading the comments as well. Okay, so so those are our batches. We define our batches, and now we're going to run the computation graph. So so for our total loss, we'll define our total loss, and then our training step, and then our current state. So remember, we defined these things beforehand. So right now what we're doing is we are going to just run what we had beforehand inside of the computation graph using the session.run function. All right, so then define our total loss, our training step, our current state, and it's going to give these values for each state, right? So for each iteration of our training. Predictions, series, boom, 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 boom. What else? And then feed dict. So feed dict, so the feed dict is how we feed in those placeholders that we defined beforehand. This is how, once we define those placeholders, we have to on current, thank you. So the feed dict is how we define those placeholders. This is how we feed in those placeholders. Okay, so then our batch X. Okay, and then batch X, and batch Y, placeholder. Okay, we've got 3 more minutes, guys, before we get to that Q&A. 3 more minutes. Okay, stick with me here. Init states. Okay, so we are feeding in the all 3 batches, right? So all 3 placeholder values for the state, the input data, and the output sequence, right, which is the echo sequence. This is what we do in recurrent net. We don't just feed in the input data. We also feed in the so then, okay, so we've got 5 more minutes here. So let me just. So then for our loss list, we're gonna append the loss list with every new loss that we calculate, right? So this is that loss list that we defined beforehand, and for our state, and then, right? So then for this part, I could just, paste this. It's just printing out values here, okay? And then we'll just close the plot. Okay. Okay. So let's go ahead and debug this. So for batch X in number of batches, for batch ID X in number of batches. Okay, so let's see what we got here. For batch ID X, there's no need for an equal sign. Great. What else we got here? Unexpected indent and feed dict. We have an unexpected indent, or sorry, okay. Init state, so for current state, so for init state, for current state on line 31, init state equals current state. So actually what this is current underscore state, and then init state, oh, it's underscore current state. Init state, oh, and then we need a comma here. Okay, great. Oh wait, no. Name start is not defined. Name start is not defined. What are you talking about? What are you talking about? On end IDX. Wait, I didn't define start, right? Where? Start plus truncated for batch IDX. All right, so for end IDX, start IDX. Great. What is next here? We got a lot of debugging. Oh my god. Oh my god. Okay, so hold on, baby. Start IDX. We've got. Hold on. What do we got here? You must feed a value for placeholder and shape 515. You mofo. Okay, we've got 3 minutes left here, so hold on. Let's visualize this. We got to talk about the visualization. We got to fit in the Q&A. Let's just go for it. I mean, plot is not defined. Plot. What are you talking about? Plot is not defined. plt.iof. Ooh, plot is not defined. It is defined. Oh, plot is not defined. So for plot, back here. Oh, because it's the visualizer. I didn't compile that visualizer. So compile this baby up here, and then move here, and then do this. Okay, guys, it's training. It is training now. Okay, placeholder. Okay, so it's training. Yes. Okay. Good. Good. Now, so actually, I want to stop this training because this is going to take a while. So we're going to stop the training. But what happens is, okay, so actually, I mean, this graph is kind of confusing here. So it's going to learn the mapping between both of those sequences. And so this is what it's going to output, right? I stopped the training, but this is what the output is going to look like, okay? So in this first graph on the top left over here, you see that the loss function is minimizing over time. Okay, so that's what that loss function is doing. And now, so these other graphs, you see that, so the blue represents the input sequence, right? It's kind of a weird graph, a way of, it's kind of a weird graph to look at, but essentially what's happening here is the blue represents that input sequence. The red represents the, the red represents the echoes, which is that output sequence, and the greens values represent the echoes the net is generating. Okay, Okay, so that's what that's doing. So essentially, it is remembering the mapping. There's ones and zeros. It's remembering the mapping, and by the end of it, it's going to know that mapping so well. And we don't need testing data because it's going to be the same, right? It's an echo of the same as the input. So you don't really need testing data. The point of this is to learn about the memory and how memory was incorporated, right? We did it by hand. Okay. Why are there spikes in the loss function? Great question. There are spikes in the loss function. Why are there spikes in the loss function? No, it was because what was it? It was because we're starting on a new epoch, and it's because we're generating new data. So because the matrix is reshaped, the first element in all of the rows is going to be adjacent to the last element in the previous row. So the first few elements in all the rows are going to have dependencies that are not included in the states. So the net is going to perform badly on the first batch. So it's going to go up and down until it gets to that ending point, okay? Because of epochs, essentially, right? So let's stop screen sharing, and then we'll do questions. Okay. Hi, guys. Okay, let's talk a bit. Let's ending 5-minute Q&A. AMA. What do we got here? Darshan and Luciana. Okay. So why do you use the last state from the previous run as the initial state for the current run? Because we are backpropagating through time. So we've already calculated all those hidden states during the forward pass. Okay. Hi, Siraj, for time series 5 years, Python and TensorFlow. That's a good question. I mean, who knows? I mean, who knows? It could, you know, it could run on binary silicon transistors. We've already surpassed human levels on a lot of state-of-the-art problems already, so it could very well run on that. Okay, thanks, Fernando. Have you heard about API.ai? I did a video for them a long time ago. Yeah, now they got bought up by Google, but I know people who work there. Thank you, Alpha. Yes, kudos to the community. The chat is becoming more and more informative each session because the reason the chat is becoming better is because we are growing at 4,000 engineers a week. We're growing very fast. We're growing faster and faster. And part of it is because of my videos, the quality, but the other part is because this field is growing so fast. Globally, we are all on a rocket ship, okay? So this community is growing fast, and if we define the culture of this community early, this culture of informing each other, of helping each other, okay, it's gonna propagate forward in all directions. Okay, we are growing so fast. We're growing so fast. Thanks, Paolo. Okay, so I'll take 3 more questions before we end the session. Session on Q learning, Sangram, great idea. I'm gonna have one after this course is, well, I'm actually during this course. I'll have a Q learning session during this course. 2 more questions. I am behind the curriculum, okay. It's over 9. Thanks, Shihao. How impactful do you think an ML-specific chip that can let people train networks much faster without needing a centralized system, like you mentioned earlier? How impactful? Guys, so training in general, there's a huge space for opportunity around distributed training services. So if you can, you know, we all have a lot of computing power that just lies idle. Our laptops, our desktops. If someone can leverage this and create a distributed computing network where people get paid for lending their computing power to TensorFlow or whatever, it's going to make them a lot of money. It's going to make people a lot of money. And this is an example of one of those jobs of the future. As automation engulfs all labor-based jobs, we're going to need new jobs. And one of these jobs, besides outputting data, is to let people use your computing power. As the necessity of computing power grows over time, this is going to be a more and more important thing. And it shows why we need that, because AWS went down, and a lot of services that we use went down with it. It shows the bad part of centralized systems. 2 more questions, actually. Hey, Suraj, can you explain how to do TensorFlow in distributed mode? Yeah, later on, not right now. Can a neural net change its size or structure like hidden layers? Hold on, that question went away. 2 more questions. Any plans on making videos related to Alexa Playground? No. 1 more question. How to get the optimized hyperparameter? How about RNN for learning hyperparameters too? So guys, right now, so if you saw that interview video, that really quick questions I did with Dan Monet, on the TensorFlow team, he had the same idea, and I had the same idea, and a lot of people, we just all kind of have the same idea, that learning ideal hyperparameters and learning model architectures and learning which model to use, learning about learning is what's hot right now. We're all trying to figure out how to best do that. So that is what is everybody's kind of focused on right now, learning to learn. So it's a great question. We don't know the answer. We have some strategies, you know, like grid search and random search, but there's a lot of space for improvement. A lot of discoveries can be made, okay? So that's it for this session, okay? And I'm gonna go, but before I go, I should probably end this with a wrap because nobody asked for it, but I just wanna do it. Somebody say a topic and then we're gonna go. 30-second wrap, because I love to do it. Someone say a, whatever subject I see first, I'm just gonna go for it, okay? Wrap, how do we use the model we just built? Use it, I mean, you can use it with a one-line function. I'm learning a lot, thank you. Thank you guys for being here. Okay, can you get some intuition, backpropagation? Ones and no's map to O's and ones. Inputs go in, add weights, get sums, pass that shit to my sigmoid function. Get that error, what's real in prediction, and that's why I use gradient descent. It gives direction and it doesn't pretend. Update weights and repeat 10,000 times. Outputs are lit, I'll be doing just fine online. As I do it now, I do it live in the future, cause I'm a loser, not really, I'm a winner. That's it. I'm from the whole place, San Francisco. Yo, stop rapping. I can't because I got a flow. Don't be homophobic. No, that was wrong. Anyway, okay. So please don't. Okay. All right, guys, that's it for this live session. Thanks for tuning in. We're going to keep going with this every single week. We are on a warpath to solve intelligence, and we will keep going every week, and we will feel to learn. We're going to learn the shit out of everything. It's going to be awesome. So stay tuned. We got videos coming out. We're going to increase video output. It's going to be awesome. Love you guys, and for now, I've got to minimize my losses. So thanks for watching.